Okay, so continuing along these notes, I want to talk about generating new things, which when I say things, I mean rings and ideals from old ones. The idea of generating rings is just here kind of for completeness, and it's sort of unfortunate that I chose to separate the notation the way I did, because I'm using this sort of bracket notation for generating rings, the way that we generated groups or subgroups from sets. Um, and I'm using this round bracket notation for generating ideals, but later on in the notes I swap to this angled notation for ideals, and we actually never really use this generating rings bits for the most part. I mean, you use it a little bit, but not a whole lot. So let me briefly talk about generating rings, and then we'll talk about the ideals, which is the important part. So for rings, the general picture is this: we have S subset of R. Again, just a ring, right? No additional assumptions. So one way of generating a ring from S, this almost always works for algebraic structures, is just to take the set of things generated, and I think in my well no yeah I think in my scribblings over here I'm going to swap this notation. Okay, just hopefully it won't confuse you, but then it'll be consistent with what I end up doing later. So I'll say S, right, is the intersection of all those, say R prime, such that S is a subset of R prime, uh, is a subset of R, I guess, right? So I'm just looking at, and what I mean here, this subset, I really mean subring. I don't know. Let me borrow the group notation and write it like that, right? So here I mean R prime is a subring. Okay, if we intersect rings, if you think about the axioms, all the axioms, as we intersect things down will remain true, right? So I mean, all we would need to show, right? So whatever this set is, I mean, what do we know about this set? We know that S is contained in this, right? And that's supposed to be contained in R, right? And what would we need to show about this set? Well, we would need to show it's closed under multiplication and addition, and that it contains 0, right? Zeros in all of those, so it definitely contains 0. Um, every one of those is closed under addition, so the intersection is closed under addition. Every one of those is closed under multiplication, so it's closed under multiplication, right? So it's kind of for free in some sense, right? And this will definitely be the smallest subring containing S, right? Because we've intersected all subrings that contain S. So that's definitely the subring generated. But it doesn't really help, given a set S, how do I actually generate this thing, right? So it doesn't really answer that question. And so that's done this other way. We've seen this stuff before too, like this is kind of like spanning and vector spaces and stuff, right? So what I'm actually going to do here is look at the sum of all I equals 1 to n, so finite sums, right? Wi, where Wi is a product of elements of S, is a product of elements of S. Okay, so we were generating groups before, we kind of called these words, and I guess that's probably why I was using W here, because I need these being words from S, right? And then clearly, right, so first of all, uh, any ring that contains S has got to contain all these things, right? Because everything in S is sort of a simple word. There's just the thing, right, and a sum of just that one thing, right? I mean, if S is an S, right, then one of the sums I'm looking at here would be like the sum I equals 1 to 1 of S, right? Just S, right? So this is just S. So that would definitely be in the set. Okay, so get rid of that. So this thing definitely contains S, and if you think about it, it's certainly closed under addition, because if I add these things together, then I just get a bigger sum, right? So it's definitely closed under addition. And if I multiply, well, so now maybe this requires a little bit of thought. I have these words, Wi, and I've got some other words over here. I'm just going to call them words because it's easier. J equals 1 to, let's say, m of, let's call it u sub j, right? When I multiply these things out and use distributivity, what are the terms going to look like? Well, they're going to be, the sum of a bunch of things that look, in fact, I guess we can just write it down, right? So wi summation j, right? wiuj, right? Just those. But these are again just products from S, and this is just a bigger sum, right? So it's definitely closed under addition and multiplication, right? So this definitely works, right? So that's the thing. And I don't think there's no real way of simplifying this construction. It's kind of a mess. Things work out much better for ideals. It's kind of interesting. So even when I have two rings and I want to look at R plus S, right? So we could look at this as a set, right? So that, just the things in R, and if we were doing just the additive group, we would have an additive group. It would be done, right? So this would be the set of R plus S, such that R is an R and S is an S. Oops, little s is in big S, right? So like that. That worked for the groups, but then we go to do multiplication, right? This is not necessarily closed under multiplication. So we have like R plus S, and then R prime plus S prime, right? And so what's that going to get us? What's going to get us R prime, let's say RS prime, SR prime, SS prime. Okay, so well, this part is in R, this part is in R, right? But this part here is in RS, right? And this part here is in SR, right? So we're kind of out of luck there. We just have to put all that stuff in. This gives you a hint at why ideals are better, because when we're in ideals, right, these things just fall into the ideal, right? The ideal just kind of eats up everything. Anyway, so even when you want to define R plus S, right, as rings, right? So R plus S, oops. You could say it, well, it just is the ring generated by all the sets, all the things R plus S, right? And of course, actually, that's just exactly the same as the ring generated by R union S, right? So it's like that. Let's see. Similarly, I guess, R times S, right? There's nothing really nice about R times S. So basically, when you're talking about rings, you're just sort of stuck with this brute force general building of rings, right? We had kind of had this with groups too, right? There wasn't a really easy way to build groups. You looked at all the words and you simplified and did stuff like that. Ideals turn out to be nicer. So let me just clear all this stuff out. And much more important, so let's go on to ideals. So when we're looking at ideals, so first of all, same kind of thing, right? If I have S subset of R and I can look at the intersection of all the ideals in R that contain S, that's definitely an ideal, right? So everything, same kind of proof works, right? But now let's look at generating ideals, okay? So again, suppose I have S subset of R, and right now I'm not assuming anything. And I want to generate, the smallest ideal containing S. Well, what kind of things does it have to have? It has to have all of S in it, right? And moreover, it has to be closed under multiplying on the left by R and on the right by R. So it has to have RS and it has to have SR, right? So it has to have those things. And then it has to have, RSR. Let's see, I might have, let me see what happens here. So I might have oversimplified this some. So if I take things in here, right? So what I'm saying is I just take the union of these things. Let's see, I think maybe we're okay, right? So we take the union of those things, and I look at the sum of AI, where AI is in the union of those things. Now I'm looking at sums, right? So this is like linear combinations, right? Sorry, let me get rid of that. Let me get rid of that. So yes, I'm making this claim that this is that. So I want to show this is an ideal, right? It's definitely true that S is in here because I'm just throwing S in by brute force, right? Definitely closed under addition, so that's good. Is it closed under, yeah, is it closed under multiplication by R and S, right? So if I take something in here, so what kind of things will it be? It'll be things, it'll be, let me just take sort of a generic 4-term thing, right? So it might have an A, which is an S, plus it might have an R, let's call it A naught, right? And it might have an RA1, so that'd be like in there. It might have an RA2, sorry, an A2R, so that would be in there, A2R. And then it might have a what, A3, so plus A3. Oh, sorry, oh, I can't use the same R. I gotta be careful here. So this is, let's say this is R1, let's call this R2, and then we'd have like an R3, A3, R3 prime, something like that, right? So that's sort of a term. Now it might be a sum of things like this, sum of things like that, sum of things like that. Now, so if I add two of those things together, I definitely get back to one of those things, to something that looks like that, right? If and by the way, I'm not saying that these are just four term sums. I'm just saying that, this is sort of a generic. I mean, this would really be a sum of things like that, sum of things like that, sum of things like that. Now, if I multiply by r, right? Let's take an arbitrary r. So I multiply by r on this side. Well, then this thing becomes something in rs. This stays in rs. This stays in rsr. This stays in rsr, right? So the whole thing drops down. So doing this puts this whole thing into rs union rsr. So that's still in there. And it's still a sum of things in there, so that's in there. And if I multiply by the other side, on the other side by r, then the same kind of thing happens, right? So if I multiply over here by r, right, then I get a naught r. So this, well, so let me just do it like this. So this becomes in sr, and then this is in rsr, and this is in SR, so an SR again, and this is an RSR, right? So this, right? So multiplying by, on the left by R puts me in RS union RSR, and multiplying on the right puts me in SR union RSR. Okay. So this set is closed under multiplication on the left and the right, right? So this is definitely easier to define than it was generating a ring in general. Good. Now, okay, now if we have unity, so now here's where things get a little bit interesting. So if we have unity, right, then of course I could just take one for an element of R, right? So these two things, oops, would get absorbed into that, right? So if I have unity, I can just generate S by taking the sums, AI. I could probably make this notation better, where AI is in S union RSR, right? So that's a little bit simpler. And if I had commutativity, I can make S, and this could be the set of all sums, where AI is in S union RS. And I could replace that by SR, because I have commutativity, so it doesn't matter, right? So this is unity. If I have unity, if I have commutativity, if I have both, right? So commutative ring with unity, then S just turns out to be summation, set of all summation AI, such that AI is an RS, right? Because again, because I have unity, I don't need to put the S in there. Oh yeah, I don't need the S in here either. Yeah, what am I doing? I can get rid of that S, right? Because I can make both sides of the R's one, right? I have one, right? So then I can just put RS like that. And that's really convenient, right? I mean, so look, this is really nice, right? So the ideal generated by S is just RS, right? That's really simple. And it could be SR, it doesn't matter because we have we have both, right? Commutative and unity. So so things don't get simpler than that, right? That's kind of nice. I had to pause for a second because I was like, why doesn't this work when I'm just generating rings? But it actually is important that we're multiplying by the whole ring out here, right? Because, I mean, what happens when we generate rings, I mean, I've already erased that, is you generate a little bit more stuff that's contained in R, but not all of R, right? And so you've got some new things, and then you multiply those things in, and you're getting more new things, right? But in this case, you're just sort of multiplying by everything on the left and everything on the right, right? So it just sort of takes care of that, right? So doing it with the ideals is just simpler, strangely enough, right? It's kind of an interesting fact. As one subcase of this, again, so suppose R is commutative with unity. I need to call these things like some things to make it easier to say. Then we just saw that if I had an S, which is the subset of R, and I want to generate the ideal, smallest ideal containing S, right? Then I just had to do RS. So that's really nice. So in particular, if I just have a single element of R, right? So just a single element of R, Then the ideal generated by that single element, right? We're going to denote. Let's see, and I said I was going to change my notation, so I'm going to use what I use later on in the notes, right? Well, at other places in the notes and in your homework and stuff, and what the book uses, right? So the ideal generated by just that single element S, right, is literally just RS. I mean, that you can't get better than that, right? And in fact, this is called a principal ideal. These are going to turn out to be really important. Because we will have rings where every ideal is principal, and in fact Z is one of those, right? So and that turns out to be followed from the Euclidean algorithm, um, and and other very important ideals that we have will be like that. Okay, and then more generally, right? If S consists of finitely many things, S1 through Sn, right? So if we're in that case, right? Then the ideal generated by S, right? Again, we're commutative with identity, right? So this will just be, R S1 plus R S2. So really, really simple. This is a lot like what we had going on when we were doing vector spaces, right? So RSN. And so you could write this as S1 plus dot, 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 plus Sn, right? Like that. So it's just that simple summation of those ideals, right? So those ideals generated by single elements. So this is really really convenient, right? Really nice. Good. All right. So a little bit more. I guess this is actually so that all comes before the section on algebra of ideals. Even though I just told you how to do plus, right? Oh no, I just told you how to generate. I haven't even told you how to do plus yet, right? So this is really nice, right? For ideals, I plus j is literally just the set of all a plus b. So literally the set, the usual set operation here. So it's a plus b, where a is an I and b is an j. So you can't get any simpler than that, right? And the point is that if I multiply on the left and right, so first of all, this is clearly closed under addition. Because if I take two of these things, I mean, let's just do it. If I have a1 plus b1 plus a2 plus b2, right, then clearly I get here a1 plus a2 plus b1 plus b2, and so that's definitely in there, right, because it's got that form. On the other hand, if I multiply, on each side by r or something like that, so I have r a plus b. Well, this is, ra plus rb, right? But this is in A and that's in B, so it's still in there. And same thing on the right, right? So addition of ideals, you just literally take the set of things added together, where the things are coming out of the set. So that can't get any simpler than that. With ideals, we can multiply. So now this is trickier, and this will actually be important. So ij is the ideal generated by all the products ij, right? So here you have to be a little bit careful. So this is not, so when we talk about the ideal ij like this, it's not just the product of things and product of something in I and something in j. Literally from what we did above, right? It's going to be the summation. It's a little easier than what we did above because these are ideals, right? So let me do something about this. So it'll be the summation of things ai, bi, where ai and ai is in I and bi is in j, like that. So why do we need that? We needed a slightly more complicated thing, right? I mean, up here when I was generating ideals, I had to throw more stuff in there, right? Why don't I need to do that? Well, if I multiply on the left right here, if I take such a term, right, and I multiply on the right by r, right, well, that r just gets absorbed, right, into those things, and that stays inside of I, right? Similarly, if I multiply on the, I said right, if I multiply on the left by r, if I multiply on the right by s, that'll get absorbed into those b's, right? So I don't need that extra stuff. I can just say literally, if these are ideals, then the things generated is just the sum of the products of the terms. So that's kind of nice. So that's even simpler than what we had above. Let's see, what else? We can certainly take intersections of ideals. So I intersect j, right, is an ideal. That's easy to check. It's also easy to check that I union j is not an ideal in general. I mean, all I need to do this is come up with an example, right? And so if I take like 5z, which is an ideal of z, and 7z, which is an ideal of z, and I look at 5 plus 7z, right? Then actually, let me think about that. Do I get, so I was going to say I don't get 12z, so maybe this is a question. Do I get 12z? Oh, sorry. That's not what I'm trying to do. Plus is good. No, that is good, right? In fact, that's nice, right? Yeah. I mean, let's see. This is 12z, right? Okay, that's not what I was looking at, right? If I look at 5z union 7z, right? This is, whatever, right? It's not an ideal. Okay, so generally ideals are not closed under unions. So if I want to look at, if I wanted to make some sort of ideal out of this, I would have to look at the things generated, right? It's like that. So then we're going just sort of dropping back to how we generate things. Oh, and in fact, I have here as a statement that this is going to be equal to I plus j, right? So I guess the claim there is that so it's certainly the case that I plus j contains I union j. Remember, 0 is contained in each ideal, right? So I can just make one of the things 0, and I can put 0 over here and add anything from I to it, so I get I. On the other hand, if I generate an ideal from I union j, well, it's got to contain I, it's got to contain j, so it's got to contain all summations of those things, so it's got to contain that. Okay, so there we go. We got something useful there. Yeah, one important thing. Let me just scroll further down. Is that notice that this is important to keep in mind. So in general, ij is contained in I intersection j, right? Because remember, if I multiply on the left by j, I stay in j. If I multiply on the right by anything in I stay in I. So everything in here is in I and j, but it might be strictly smaller, and we'll see examples soon to clarify that, even inside the integers, just to make that more clear. But in general, the relationship is that ij is contained in I intersect j is contained in I union j is contained in I plus j. Okay, I see I'm actually going to run out of time pretty quick for this video here. I'm restricted to 30 minutes, which is good for you guys. It's kind of interesting that this, we have this whole algebra now, right? So we have I plus j plus k equals, I plus j plus k, right? We can show things like that, right? So looking at ideals as objects now, we have associativity, right? We have ijk equals ijk. These are easy to show, right? So again, we have associativity. We have I plus, the 0 ideal is a trivial ideal, right, is equal to the 0 plus I is equal to I. So we even have an additive identity, right? We have that in case we have a unity, right, we have Ri equals Ir equals I, right? So this is if R has unity. So R is like the unit, right? So R is like the unit ideal. The only non-proper ideal is like the 1, right? What we don't have is we don't have any kind of inverses, right? So we're not in a situation like that. So we have associativity and we have identities. So there are these things called semigroups. So we could say we're looking at a semigroup of objects here. Oh, and there's a distributivity. Yes, I mean, you can keep going, right? There's all sorts of laws here, and I guess we'll use these. Jk equals ij, ik, right, and vice versa. J plus ki, equals ji. Now remember, there's no commutativity in general, so you got to be a little bit careful with what you do here. And I guess we have one more that's useful. I intersect j plus k will be I intersect j plus I intersect k. Okay, so anyway, these are all good like exercises to do. Not difficult, but good exercises. Let's see, about to run out of time. It's a little bit of stuff here about ideals in R and extending them, looking at the polynomials built over that ideal. That'll be an ideal in Rx, okay, and we get this kind of nice isomorphism. I don't know if we use that, but if we do, we'll come back and talk about it. And let's see, is there anything else? There's another thing here about pullback ideals. I guess I don't think we use this. I'm gonna just skip it. And I guess I'm gonna make another video for the Chinese remainder theorem. So that uses a bunch of this kind of algebra stuff here for a specific thing, which is an important thing to know. Okay, so I will stop this one.